In this video, we're going to talk about how you charge an RC circuit. The real question we're trying to answer is, what happens when a source is included? Let's draw the circuit first. I now have a voltage source, and we're assuming this is turning on at t equals 0. So once again, we have that switch, and this switch is closing and completing the circuit at t equals 0. And then I have my resistor and capacitor. Now, in this case, we still want to know Vc as a function of time. To make things a little bit simpler, we're going to assume that Vc of 0 is 0. This may not necessarily be the case, but it doesn't really make our analysis any significantly more difficult. It just makes our constants a little bit easier to find. Like before, we're going to use KCL. And we're going to do KCL here, at the node that connects the resistor and the capacitor together. Using KCL, assuming that I have a current this way, and this way as well, so here's a node, and we're assuming that there's current flowing out of it, then I have Vc minus my voltage source over my resistor, that's this current here, plus C dVc by dt equals 0. I'm going to rearrange this because we're going to need the rearrangement later. Simply multiply by R. And what I end up with is RC dVc by dt plus Vc, and put V on the other side. So this is an equation we're going to be working with. Once again, I'm going to leave the details to a math class. However, because we have this added input, Vc of t will actually have a different form. So we have k1 plus k2 e to the st. We need to know k1, k2, and s. In order to find k1 and k2, we use the initial and final conditions. Once we know them, we can plug it back into this fundamental equation here and solve for s. So, let's use our initial condition, or our ICs. Initially, Vc of 0 was assumed to be 0, and that'll be equal to k1 plus k2 e to the 0 times s. And remember, 0 times s and then raised e is going to give us 1. Therefore, we know that k1 is negative k2. But we're not done, because we still have two equations and two unknowns. We can look now at the final conditions. As t approaches to infinity, what happens? Well, let's think a little bit about our circuit. And I've closed the switch here so that we don't need to worry too much about it. We have a voltage Vc across the capacitor. The first thing I'm going to promise you is that Vc is always less than or equal to the supply voltage V. The reason for that is because V is my only source of energy in the circuit. My resistor certainly doesn't supply any current, and my capacitor also doesn't supply any current. It only stores it, and then releases whatever it's stored. So the maximum Vc can get at is V. Now let's see what happens if Vc was not equal to V eventually. If Vc does not equal V, then I'll have a voltage here, Vc, and a voltage here, V, that are different, and therefore current will flow. But if current is flowing, then the voltage will be changing in the capacitor, and in steady state, I won't have that. Therefore, we can make the conclusion that Vc at infinity, that is to say, once time has gone on for a very long time, is equal to our voltage source V. this implies that K1 is equal to V, because we'll have e to the power of something. Turns out that something will have a negative exponent. But let's prove that before we can really agree with this statement here. Our next step is to find S. So, we are claiming that our voltage is going to be of the form Vc of t is V minus V e to the st. I'm now going to further claim that S is equal to -1 over RC, just like before. Let's see if we can plug it into our original equation and see if that comes out. So, in our original equation, plugging this in for Vc and taking the derivative, we'll end up with negative RCS times V e to the st plus V minus V e to the st is equal to V. So the first thing I'll do is subtract these V's away, and then I will divide and rearrange. And what I'm left with is RCS is -1, or S is -1 over RC, which, if you remember from last video, is -1 over tau. So, we're left with Vc is V minus V e to the negative t over tau. There's only a very minor modification we had to make in this charging case. What does it look like? There's T, and there's Vc. Our Vc starts at 0, and then increases until eventually it reaches a steady state value of V. And this is the RC charging.